If you could just point a rocket at Jupiter, how long would it really take to get there? And why is that answer so much more complicated than it seems? Picture yourself staring up at a pale dot in the night sky and wondering, how long would it take to reach that distant world? It sounds like a simple question, but asking it opens a door to a universe of staggering numbers, wild engineering puzzles, and choices that can make or break entire missions. You might think space travel is just about going fast or crossing enormous distances, but the reality is stranger. The clock in space does not tick like ours. Every trip to the giant planets is shaped by a tangled web of moving targets, rocket fuel limits, and the need to slow down. Sometimes the fastest path is not the best, or even possible. Misunderstanding this cosmic logic is risky. It can make us underestimate the true challenges, costs, and timelines of exploring our solar system. The stakes are massive: billions of dollars, decades of work, and our future as space explorers all hang on getting the timing right. So, what really decides how long it takes to reach Jupiter, Saturn, Uranus, or Pluto? Let's dive into the mechanics that make space travel such a peculiar dance, where patience and planning matter as much as raw speed. To unravel this mystery, we need to break down the puzzle, starting with the ever-shifting distances and orbits that set the stage for every interplanetary journey. The outer planets are more than distant dots. They hold secrets to life, cosmic history, and maybe even our future. When we talk about exploring Jupiter, Saturn, Uranus, and Pluto, we're not just talking about cold rocks orbiting in the darkness. Each one is a world brimming with mysteries that could change how we see ourselves and the universe. Jupiter is the giant, the king of the solar system. Its massive storms, like the Great Red Spot, rage for centuries. Jupiter's magnetic field is so powerful, it could fit more than a dozen Earths inside. But what's even more exciting is its collection of moons, dozens of them, with Europa, Ganymede, and Callisto possibly hiding liquid oceans under thick ice. These worlds might be the best places to search for alien life in our own backyard. Then there's Saturn, famous for its stunning rings. These icy bands are not just pretty, their origins are still a cosmic puzzle. Saturn's moons, especially Titan and Enceladus, have grabbed scientists' attention. Titan has lakes of methane and an atmosphere thicker than Earth's, while Enceladus sprays water and organic materials into space, possibly signs of a hidden ocean below. Uranus is the oddball. Unlike any other planet, it rolls around the sun on its side, its axis tilted almost 90 degrees. Its blue-green color comes from methane in its atmosphere, but its real mysteries are inside, a strangely lopsided magnetic field and barely any heat escaping from within. Uranus is a puzzle waiting to be solved. And on the edge of the solar system, Pluto, once called a planet, now a resident of the Kuiper Belt. It was exiled from the Planetary Club, but when NASA's New Horizons probe arrived, Pluto surprised everyone. Despite being billions of kilometers away, it has ice mountains, blue skies, and a complex story that only deepens the farther we look. The distances to these worlds are staggering and always changing. Orbits are not perfect circles, so alignments mean the gap between us and these planets can vary by hundreds of millions of kilometers. Sometimes a planet is as close as it will ever be. Other times, it's far across the cosmic highway. Every mission has to plan around these shifting windows. Skipping these worlds would be like tearing out whole chapters from the book of our solar system. The risks aren't just scientific, they're about ambition and the kind of future we dare to imagine. Why do scientists care so much? Because these planets and their moons hold clues to where water and organics can survive, how planets form, and whether life could exist elsewhere. Missing out on them means missing out on answers to the greatest questions humanity can ask, about our origins, our place in the cosmos, and maybe even where we could live in the far future. But even with all this motivation, exploring the outer planets isn't as simple as aiming a rocket and firing. The real challenge comes from the silent choreography of physics, timing, and limited resources, a dance that determines if a mission succeeds or fails. In space, speed alone is not enough. In fact, it can be a trap. When it comes to reaching the outer planets, the journey is shaped by a complex web of moving targets, gravity, and hard choices. The time it takes is not just about how far you have to go, but how, when, and why you make the trip. Earth and each of the outer planets are racing along separate tracks, orbiting the sun at their own speeds. That means the distance between us and, say, Jupiter or Saturn is always changing. Sometimes as close as 587 million kilometers, sometimes nearly a billion. Timing your launch is everything. If you miss the perfect window, your journey could take years longer, or even become impossible with today's rockets. But even the best timing is just one part of the puzzle. The quickest path is rarely a straight line. Instead, spacecraft often rely on gravity assists, slingshot maneuvers around planets that boost their speed without burning extra fuel. These moves demand precision, planning, and patience, often adding months or even years to the route, but saving precious kilograms of fuel. Arriving too fast, though, creates a new problem. If a probe speeds up to get to its target in record time, it may have so much momentum that it can't slow down. Instead of going into orbit and studying a world up close, it just shoots past, gathering only snapshots in a blink. This is why missions like Pioneer and Voyager, which zipped by Jupiter in less than 2 years and Saturn in a little more than 3, could not stop to linger. Compare that to missions built to stay. Galileo took almost 6 years to reach Jupiter, using several gravity assists to ensure it arrived at just the right speed, slow enough to be captured by the planet's gravity. Cassini, heading for Saturn, spent 7 years weaving through the inner solar system, borrowing energy from Venus and Earth to make its arrival possible. New Horizons set the speed record to Jupiter, racing there in just over 1 year, but it too was just passing by on its way to Pluto. The faster you want to go, the more fuel and power you need, but there's a catch. More fuel means a heavier spacecraft, which, paradoxically, often means slower acceleration and more risk. Push too hard and failures get more likely, and the cost can balloon into billions of dollars for each gamble. Misjudging these variables is not just an academic problem. It can waste decades of work, destroy spacecraft, and, in the case of human missions, endanger lives. Billions of dollars and the hopes of entire generations hinge on mastering this cosmic calendar. Now imagine sending people on these journeys. Suddenly, you have to carry not just fuel and instruments, but food, water, life support, and radiation shields. The mass explodes, and every extra kilogram makes the mission even harder. A human voyage to Jupiter would take about 6 years, to Saturn about 8, and to Pluto more than 25. Every year means more supplies, more psychological strain, and more things that can go wrong. But understanding the real reasons behind these travel times is only half the story. What does this mean for the future of exploration? And how do we decide which worlds are truly worth the wait? To see where we're headed next, let's look at how upcoming missions and new propulsion ideas could rewrite the rules of reaching the outer planets. Every year gained or lost on these journeys doesn't just shift a schedule. It rewrites our scientific priorities, our sense of possibility, and even the stories we'll tell when we come home. Right now, the most ambitious outer solar system mission in the works is the Uranus orbiter and probe. If all goes smoothly, its launch window opens in the early 2030s. The price tag is set at about $4 billion, and the trip itself will last somewhere between 13 and 15 years, just to arrive and begin the real science. But those years in transit aren't empty. Every mission, every delay, gives time for new technologies to mature. The experience gained on the Moon and Mars, better spacesuits, advanced habitats, more robust support systems, will be the foundation for surviving and working farther from Earth than ever before. Yet, each mission comes with a trade-off. Choosing a flyby means we get only quick snapshots, a fleeting look with limited detail. Opting to orbit promises deeper science, maps, atmospheric analysis, and long-term discovery, but demands years more in planning, patience, and budget. It's a constant balancing act, speed versus science, time versus detail. And those timelines? They stretch far beyond the launch countdown. New Horizons took more than 9 years just to reach Pluto. For Uranus, from the earliest concept discussions through engineering, launch, the long cruise, and finally receiving the first data back, the wait can easily stretch over 2 decades. An entire generation of scientists might dedicate their careers to a single mission, sometimes retiring before the first results are even in. The stakes are more than just scientific. For human crews, every extra day in deep space raises psychological and biological risks. Radiation, isolation, resource limitations, all compounded the farther we go. Even for robotic probes, patience is a necessity, not a choice. Meanwhile, our cosmic priorities keep evolving. Studying Uranus and Neptune, these overlooked ice giants, does more than satisfy curiosity. Their mysteries echo in distant exoplanets circling other stars, offering clues to worlds beyond our own and reshaping how we see our place in the galaxy. But in this high-stakes waiting game, a single miscalculation, a delayed launch window, a failed maneuver, a funding cut, risks not just data lost, but years, careers, and billions evaporating into the dark. The cost of patience is high, but sometimes the cost of haste is higher. So what can we learn and apply from this cosmic juggling act? Let's break down the practical lessons hidden in these mission timelines. Space rewards those who wait for the right moment and punishes those who rush. In the vastness beyond Earth, patience is more than a virtue. It is survival. The universe does not care how fast you want to get somewhere, only whether you are ready for its challenges when you arrive. Mission timing is a cosmic choreography. Space agencies must wait for planetary alignments that line up like dancers on a stage, taking advantage of gravitational assists and planning routes that match their goals and their resources. Sometimes the fastest path is not a straight line, but a carefully plotted arc that uses the gravity of Venus, Earth, or Jupiter to slingshot a probe further and faster than rockets alone ever could. The truth is, a slower, indirect route is often the only way to actually reach your destination. Arriving too quickly means you fly right past your target with no chance to slow down and explore. That is why missions like Galileo or Cassini took years, looping around planets for gravity boosts and arriving with just the right speed to be captured into orbit. In space, the question is never just how fast can we go, but how well can we arrive? Impatience in space travel is not just risky, it can be catastrophic. Rushing means wasted fuel, missed opportunities, and sometimes total mission failure. The lesson is clear. Patience and careful planning are not delays, but investments. The greatest discoveries, oceans beneath icy moons, rings of Saturn, the secrets of Pluto, were only possible because engineers and scientists allowed years, sometimes decades, for the right moment to come. These are not just lessons for rockets and probes. Long-term thinking, adaptability, and knowing when to wait pay off, whether you are tackling space or the challenges of everyday life on Earth. The journey's true value is not just measured in arrival, but in what you bring back. Stories, data, understanding, and inspiration for the next leap forward. So next time someone asks, how long does it take? Remember, in space, what counts is not just the clock, but the courage to wait for the right window, and the wisdom to seize it when it opens. The honest answer is not a number. It's a story. Now, let's see how these cosmic rules played out for the real missions to Jupiter, Saturn, Uranus, and Pluto, their routes, their timelines, and what they teach us about journeys farther than most can imagine. When we first ask, how long does it take to reach Jupiter, Saturn, Uranus, or Pluto, it feels like we're searching for a single definitive value, a magic trip time. But as we've seen, the real answer weaves together shifting planets, patient engineering, and human ambition. It's a story of timing launch windows, borrowing energy from other worlds, and sometimes slowing down on purpose so we don't miss our chance to explore. Space travel's timeline is not stamped in stone. It bends and flexes with every mission's goal, every planetary alignment, and every risk we're willing to take. The difference between a fast flyby and a careful orbit is not just a few months. It's a statement about what we value: speed, safety, or scientific discovery. The journey to the outer planets becomes a mirror, reflecting our own patience and willingness to wait years, even decades, for a single window to open. So the next time you look up and wonder, remember, the timeline is not just measured in days or years, but in the ambition to keep going, even when the finish line is far beyond the horizon. In the end, understanding how long it really takes to journey across the solar system reshapes our expectations, not just for rockets and robots, but for ourselves. We see that exploration is as much about choreography as it is about chemistry and fuel. It's about playing the long game, working with the universe's own schedule, and accepting that sometimes the smartest path forward is the slower one.